In this work, we introduced GeoVLN, a novel framework learning geometry, enhanced visual representation based on slot attention for robust visual and language navigation. Most existing works solving room-to-room VLN problem only utilize RGB images and do not consider local context around candidate views. To address this limitation, our GeoVLN compensate RGB images with the corresponding depth maps and normal maps estimated by Omnidata, providing enhanced visual inputs. The RGB information surrounding the candidate view is aggregated by a local-aware slot attention module. Technically, we introduce a two-stage module that combines slot attention and clip model to produce geometry, enhanced representation from the input. We employ VLN BERT to learn a cross-modal representation that incorporates both language and vision information. Additionally, we introduce a novel multi-way attention module that encourages different phrases of input instructions to exploit the most relevant features from the visual input. Visual and language navigation involves humans providing natural language instructions to an agent, and then the agent automatically makes decision about the next move based on past and current visual observations. In the discrete room-to-room navigation task, the environment is defined as a connectivity graph where the agent can move between vertices along the edges. At each viewpoint, the observations include 36 discretized views, among which the reachable views are referred to as candidate views. At each time step, the agent decides whether to move to one of the candidate views or to stop. Let's overview the pipeline of GeoVLN. At each time step T, our framework takes a single user instruction and a set of visual observations as input. The language input is processed by BERT encoder to obtain a sequence of word embeddings and a global latent state street. The visual input consists of 36 view RGB images, and we additionally estimate the corresponding depth maps and normal maps using Omnidata. We design a two-stage module to process these multimodal observations and acquire a geometry-enhanced visual representation. Given both the global latent state and vision representations, the final action is predicted using a multi-way attention mechanism. Next, we will provide detailed explanations of how the two-stage module and the multi-way attention module work. In the two-stage visual representation learning, we initially employ the clip image encoder to extract feature vectors from all the visual observations. We concatenate the visual features with angle features to obtain the final visual features. Subsequently, we utilize a local-aware slot attention module to encourage each candidate view to aggregate information from nearby observation views based on spatial proximity. Specifically, we initialize the slots with RGB candidate features and treat them as queries during attention calculation. The nearby views, whose heading and elevation angles differ by no more than 30 degrees from the candidate views, are used as keys and values. This process results in the slot-enhanced RGB feature. We then concatenate this feature with depth features, normal features, and view angle features, and project them to acquire the geometry-enhanced visual representation. The multi-way attention module facilitates decision-making by enabling different phrases of the input instruction to focus on the most informative visual observation, including texture and depth. We compute attention scores of SAINT using three modalities: RGB, depth, and normal individually. The final policy likelihood is obtained by weighted summation, where the weights corresponding to the three modalities are dynamically adjusted parameters related to SAINT. These weights describe the contribution of each modality to the navigation and change dynamically. We provide a quantitative comparison of our GeoVLN with the previous methods on the room-to-room dataset. Additionally, we report the results of GeoVLN Dagger, an extension of HAMT, with our newly designed modules. As shown in the table, our models outperform all baseline methods, demonstrating particularly impressive results in unseen environments. Furthermore, we conduct ablation studies. The quantitative results confirm the efficacy of multi-modal visual inputs, local-aware slot attention, and multi-way attention, thereby supporting our claims and contributions. We also include two visualization examples to demonstrate how the local-aware slot attention module aggregates local observations to candidate views. Each image in the visualization is accompanied by an attention score, indicating the importance assigned to it. Notably, the nearby images containing objects such as a pool, stairs, and handrail receive higher attention scores. This indicates that the agent successfully extracts useful features from its local neighbors to aid decision-making. These figures show how the weight coefficients of the three modalities change in a single successful navigation. In this particular case, the depth information rather than the RGB information is given the highest weight coefficient. At t equals 0, our model correctly selects the candidate view that contains the double doors. This successful choice can be attributed to the depth map, which provides crucial information about the room located behind the doors. At t equals 5, the weight coefficient of RGB increases while the weight coefficient of depth decreases. This aligns with the instruction to wait in the doorway with the double doors, emphasizing higher attention to RGB images to confirm the appearance of the door. Thank you for watching our video. Please refer to our paper for more details and visualizations.